Yeah, good morning, everyone. It's Tim speaking now. It's nice to see some old friends in here and hope you're all keeping well. To people who don't know me, I'm one of the application engineers here at Pico Technology, and together with Stuart, we're going to be running you through the training this morning. The 9400 is a slightly different product within our range, and we thought it'd be useful to try and position this for you. Obviously, we have real-time instruments and we have sampling scopes, and it's finding this middle ground and help you to try and position this. So really, we're sharing a different product story in what's a well-established oscilloscope market. What we'd like to be able to achieve at the end of this, our objectives are for you to explain the three different ranges of oscilloscopes from Pico, introduce the PicoScope 9400A series SXRTO, Sampler Extended Real-Time Oscilloscope, that stands for, which we'll be covering in more detail as we go through. I'll not be saying Sampler Extended Real-Time Oscilloscope every time. We'll cut that down to SXRTO. We'd like you to be able to understand what applications are suitable for the 9400A series. You'll see the applications are actually quite similar to the 9300 as well. We'd also like to establish in your mind what the differentiators are in that respect. I always find when I visit a customer, if I can visualize the software in my mind, it helps me position the product against the application you're talking to the customer about. So moving on to the first slide. We've said this many times before that Pico is the market leader in PC oscilloscopes, and we still believe this, and it is the modern alternative to the traditional benchtop instrument. We have three categories of oscilloscopes available: real-time, sampling, and SXRTO, and have differentiated here by the sampling technology. Looking at the real-time instrument, we have the 6000 series, which is one of our high-end real-time instruments. Under sampling, we have one of the 9300s, our sampling oscilloscopes, been with us for many years now, previously the 9200 series, and has been a fantastic product for Pico over the years. On the right-hand side, we have one of our new 9400A series products, the 25 gigahertz instrument, which is the SXRTO. And that's where our focus on the training lies today. So moving on to the 9400 and 9400A range. Yes, there's a surprise there for one or two of you with the 9400A. The 9400 is familiar to most people on the call. You can see we have the 4-channel 5 and 16 gigahertz instruments, and also the 2-channel instruments. Been with us now for quite a few years. Stuart and I have been involved with demonstrations to your customers on this, and I know that some people on the call have sold some of these, thank you, and we look forward to everyone else joining us on the call to facilitate the sales of these instruments. So the next slide is actually the 9400A series, and you can see we're actually moving forward onto a new product range here. We have the 4-channel 25 gigahertz instrument, which is in the range at the moment. We'll have a product launch coming up soon on the 33 gigahertz, and also the 6 gigahertz and 16 gigahertz instruments. The 9400 series will still be with us, particularly while there's stock available. So these will phase in over a period of time. Those of you who subscribe to the newsletters will be advising when the product launches do come forward on this one. I'd just like to have a quick look at the technologies and standards. What we're finding is high-speed electronics and communications now are evolving quickly, and everything's getting faster, getting smaller, and more energy efficient. We're seeing faster backplanes and networks, higher speed ADCs, FPGA and SERDS devices are increasing in speed. Certainly in the UK here, 5G deployment we're seeing rolling out in quite a big way. And I've already been involved in one demo with a company doing 6G research. So that's coming along the line as well. Semiconductor materials from When I first joined Pico over 12 years ago and used to see some of the PCB layouts to what I'm seeing now is just a completely different world. I'm pleased I'm retiring soon. It's gone beyond my level of understanding. Silicon photonics, again, a big area we've been involved in. Packaging changes. And if we look at the standards now, particularly for bandwidth and data centers, we've got PAM4 coming in, and we're often seeing a gigabit to the desktop as well. So everything's getting faster. So let's have a quick look where the technology gets used. If we look in the telecom sector, we have the 5G base stations, we have phones. We're typically going up to 25 gigahertz at the moment, but I expect way beyond, particularly in some of the research centers. Aerospace, we're looking here at satellites and modems. Again, I remember the days when you used to connect to the internet via a modem, a completely different method now, and looking at 12 gigahertz speeds. Automotive, obviously Pico do have an automotive division, and the test and measurement side of the business sometimes gets involved with automotive, but more in research and development. And particularly with radar at the moment, we've been involved with the 9300 and the 9400 series. So we often work alongside our colleagues in automotive on these opportunities. Medical, we're seeing down to microwave level. We've got MRI, telemetry, ultrasounds evolving. With our VNAs, we have some OEM opportunities where they've been integrated into medical systems as well. Data centers, I've already mentioned PAM4 and optical. Switches are faster, interconnects are faster. On top of that, you've got security, which all comes into this. Consumer devices, we're seeing are faster every time there's a new iPhone or any other type of phone released. We're seeing that's going faster. We have Wi-Fi getting faster, and we have anyone who has children will realize the gaming's moving much faster now. We could probably talk all day about IoT. One thing we can say, that's becoming faster. So this represents challenges to designers. First of all, if we look at signal integrity and transmission line effects, so we're seeing faster edges, higher frequencies, traces on PCBs behaving like transmission lines, not ideal wires. Signal attenuation increases with frequency and distance. Really what we're seeing, what goes in doesn't necessarily come out. We're seeing reflections, crosstalk, ringing, impedance, mismatches. These are all problems when customers phone in that we are addressing with the 9400 series. Noise and jitter as we get faster is a big issue. PCB design constraints. We will be showing a video from one of our own engineers who's using the instrument in this respect. Of course, as we get faster and things get smaller, we have EMI to consider, both in our product designs and also in interference. And this becomes more susceptible at higher bandwidths. So at this point, I'd just like to have a quick look at the key specifications and features of the 9400 series. And you'll see from the specifications how this addresses the problems that an engineer can encounter. We have instruments to help them now, going from 5 to 33 gigahertz bandwidth. We offer 12-bit resolution on the 9400 series, 2-channel or 4-channel instruments. We have an effective sampling speed of 5 terasamples per second and better than 1.5 picosecond jitter. We have automated measurements which are designed for the engineers to help them in their work, particularly looking at sine, pulse, NRZ, and for PAM4. When Stuart shows these demonstrations and applications, we'll be seeing a little more in this respect. Mask testing again gets used in pre-compliance. We have 175 masks on the instrument in the software, and if that's not enough, you can actually build your own mask as well. Histograms are a very important part of the testing as well. On the 9400 series, there is a optional clock recovery instrument. This has to be factory ordered. It's not popular because of the way the instrument works. We don't necessarily need clock recovery in the same way you would in a 9300 series, but it is there as an option. Like all Pico instruments, this is a Windows-based instrument, and we do have a documented API as well. So as well as using the PicoScope, Pico Sample 4 software, you can actually write your own software with this, and they'll be showing you where the downloads are to help you in that respect. So I think the next thing really to look at is the sampling technologies. Many of us are familiar with real-time oscilloscopes, which is the traditional oscilloscope, and in Pico we have our 2000 to 6000 series. Here we have a free-running ADC inputting data into the buffer memory. We can see the diagram on the right-hand side here, and we can see that each data point consists of a timestamp and of corresponding voltage for that timestamp. The memory buffer is circular, and when full, it overwrites. In PicoScope 7, you'll notice that there's many configurations you can have with that, and we have the waveform buffer as well. But I'm just really looking at how a real-time oscilloscope works here and how we can compare that to the other two types of instruments we offer. It also captures data constantly. You can view pre-trigger and post-trigger events in a real-time instrument. By contrast, the 9300 series is a sampling oscilloscope, and this requires a reference clock for the instrument to operate. And it takes a sample for each trigger. So looking at the diagram here, we call this sequential time sampling. And looking at the waveform going across the screen, we can see the lower frequency representation of the waveform there. And this is how it's called a sampling scope. And also, one advantage of the sampling scope is due to the lower data acquisition rate, we can use a higher resolution 16-bit ADC. So by contrast, the 9400A series, the sampler extended real-time oscilloscope, or SXRTO, is a device which has been developed by Pico Technology. It is quite a simple concept in that it works 500 million samples per second real-time sampling and then moves into the extended time sampling range. It's in this extended time sampling range, or ETS, where all the technology has been applied. And we've taken the Pico Sample 3 software from the sampling scopes and developed that into Pico Sample 4. And the instrument offers many of the features and benefits of the sampling oscilloscope. So looking at this from a slightly different perspective, this slide shows that on the 9300 series, we have a clock and we take one sample per trigger. So the 9300 builds a trace trigger by trigger. By contrast, the 9400 series uses random equivalent time sampling. We have a continuous clock and it sees pre-trigger events. And so for each trigger, we have a randomly placed comb of points. So it grabs the data on that trigger point and displays that. So let's try and summarize these two slides. It's important to understand the concept of the 9400 series. So I'm going to be coming at this from one or two different directions. So the 9400 series stores the data in the same manner as a real-time oscilloscope. It's continuously capturing and has a circular memory buffer. The key differences are in the triggering, whereas a real-time oscilloscope uses digitized triggers, such as in the 6000 series, where we have a very wide range of digital triggers. With the 9400 series, we have a separate analog circuit, and we use analog triggering on this instrument. The PicoScope 9400A, we can work in 500 millisamples per second real time and then move to ETS. No one's really going to buy this as a 500 millisamples per second real-time instrument. However, there is the odd application where that can fit into. A random time sampling is available up to 5 terasamples per second on the upcoming 33 gigahertz instrument in the extended time mode. So let's compare this to a sampling oscilloscope. The 9400A and the 9300A series are both ideal for measuring high-speed interfaces. Both require repetitive signals, both require repeating clock streams, and PicoSample 3 and PicoSample 4 software are very simple in appearance and operation. The reason being, as stated before, PicoSample 4 has been derived from PicoSample 3, as often the instruments are used for addressing very similar applications. So here are the key differentiators between the instruments. The 9400A series triggers on the input signal like a real-time oscilloscope and therefore captures pre-trigger events. Another way of describing that is we have in-channel triggering. The 9400A series moves to the extended time sampling mode once we get above the real-time sampling speed of 500 million samples per second. It has a 12-volt vertical resolution ADC compared to the 16-bit version on the sampling oscilloscope. If we now look at the 9300 series, we require a separate trigger here and we capture a sample for each trigger event. It cannot trigger directly on the signal, so therefore misses pre-trigger events. There are different ways of looking at that, and we will have a follow-on training from this, as we did with the VNA, and we'll go into this in a little more detail. But for now, the 9300 series does not trigger directly on the signal, and we can take it that it misses pre-trigger events. But watch this space on that one, we'll come back to it. The 9300 series has TDR and TDT functionality. We also have an optical input. It has a 16-bit vertical resolution ADC as well. So I'll just go back to that slide. When a customer phones in or comes into Pico, or indeed yourself, I think the first level of discussion we go through is, do they really want a real-time instrument, or could we offer them a 9300 or a 9400 series? Really, without looking, if they have repetitive signals, repeating clock streams, well, we're actually ideally into the 94 and 9300 series territory here. If they then say it would be useful to have a TDR and optical, then that's steering into the 9300 series. But today's discussion is all about the 9400 series, and one of the big advantages is the in-channel triggering. Again, Stuart and I are here and can always have calls with yourself and your customer to help qualify in the first instance. So moving on to this slide where we sell the SX-RTO against an RTO, looking on the left-hand side, the big advantage of the SX-RTO is the low cost of high bandwidth, and it shares the same advantages here of the real-time oscilloscope where we can view trigger and pre-trigger. We've got on-channel triggering, and we've got data eye-test analysis. I'm not too concerned with the middle ground here because it's applicable to to either instrument. However, I would just like to run through the weaknesses here where you can't really sell the 9400 series. If they really do want a real-time instrument, that would be the first level of qualification. Data streaming again requires a real-time instrument. Transient capture would require a real-time instrument, and serial decode. So if we take those three instances away, we can offer the SX-RTO, and we have a very good pricing advantage against most other players. So looking at these advantages, I am emphasizing here the fact that we require repetitive signals and repeating clock streams. We do go up to 33 gigahertz. The key differentiator, as in most things in life, is pricing. When the 9400 series fits the application, that's been proven either in an online demo or the customer's had an instrument to evaluate. There's a very significant pricing advantage. And starting at 5 gigahertz, we're often half the price. And as the bandwidth increases, that increases much more. Many of you will remember our old friend Mark Ashcroft, and his tagline at product launch was, "Can we disrupt the HF oscilloscope market?" And I believe we have done with this instrument. So I'd like to have a quick look now at a user scenario. A customer found you has a 100 megahertz oscilloscope. We'd rather call you and have a requirement for a 1 gigahertz oscilloscope, but for the sake of this, let's just look at this. They now need a second instrument, but ideally at a higher frequency. What we can offer here is assuming it meets the criteria for repetitive waveforms, we can offer a range of instruments from 5 gigahertz to 33 gigahertz for the high speed work. But they also have an instrument which is a backup instrument up to 500 million samples per second. So they actually have, as well as the original instrument, by buying one of the 9404As, they actually have two instruments in one here. They now have an ideal situation where they have 3 instruments for one, and you can keep that customer and increase your sales revenue. Perhaps not a typical application that comes in, but it does demonstrate the capability of the instrument. There is one application that will meet, and we'll be discussing that further in the follow-on seminar. When a customer does phone in, they're more likely to have an application, for example, PCIe or radar applications or any type of different application, and we need to go through a pre-qualification check with them in that respect. So if we now take a quick look at Pico Sample 4, it's available from our download page. The current version is 4.12. The software, this is a user interface, which you will see on download. I'm not going to talk about the user interface because we'll see more of that in our product demonstration coming up. If you go to the documentation site on the website, there's the user guide, the dreaded user guides. If anyone's like me, you very rarely use them. You get them out when you become stuck. We have a programmer's guide, and we have a quick start guide in different languages as well. There's also documentation on the site as well, such as declarations of conformity. Incidentally, if anyone's ordering one of these instruments and you do require a calibration certificate, that's a separate, please do let the sales manager know in advance of that. That's a very different document to the declaration of conformity. Pico have a GitHub site many of you will be familiar with, and we do have programming examples available on there. We also have a technical support team who are skilled in different areas and will be able to help you with any OEM applications or scripts that you need to write. We had one customer come in this morning on the 9400 requesting assistance on Python, and that's gone to the appropriate support engineer who's assisting them in that respect. Pico Sample 4 is very user configurable. We can scale up to high definition screens. We can go to an expanded touch screen, which is useful for exhibitions, where if you have a large monitor, you can then use your finger to use the touch control, and it's a real attention grabber for bringing people onto an exhibition stand. It's also very useful to show in a demo. It is slightly gimmicky, but believe me, the customers do like that. And you can also have multiple screens and resize in any direction, as you can see below. So in summarizing all of this now, we offer high performance and portable instruments from 5 to 33 gigahertz. We combine the benefits of real-time sampling, random equivalent time sampling, and a high analog bandwidth. We can draw eye diagrams with ease. We've got built-in masks. These are ideal for pre-compliance testing of product design. We have comprehensive built-in automated measurements, zoom facilities, histograms. The measurements are very impressive. No doubt Stuart will show you some of the measurements in the demonstration. The instrument's ideal for OEM integration, where we have a small footprint, 12-volt low power, and the documented API. The instruments come with a 3-year warranty, free software updates for life, and lifetime technical support. As I've mentioned previously, we will be having a follow-up session on July the 8th, where we'll be recapping on the fundamentals to make sure everyone's familiar with SXRTO and how to present that to your customers. We'll also be going up more into the architecture of how an SXRTO works, and we'll be showing a much wider range of application demonstrations.
Hello everyone, we are now going to show a short video with Adrian Carter, who is a senior hardware development engineer here at Pico, talking about how the PicoScope 9400A helps him with his work. Enjoy.
Hey, hello Adrian. Thanks for taking the time to speak with me. To start, could you briefly describe your current role within product development and the primary focus of your team's work?
Okay, my main job is designing oscilloscope front ends, so real-time oscilloscopes, particularly high bandwidth ones. I'm the tech lead on one of our teams here at Pico. Yeah.
Okay, thank you. How long have you been using the PicoScope 9400A series in your product development activities?
So one of the key parameters of our front ends is pulse response and rise time. And to measure that, you really need a very fast scope, much faster than what you're trying to design. And that's where this 25 gigahertz scope comes in. The new 25 gig one particularly is really good. I used to use the 16 quite a lot. Okay. So, you know, when you're using this to measure rise times that are hundreds of picoseconds, then it gives you a really accurate measurement. And we can look at overshoot and the pulse response to see what where we're at really. Yeah. Okay.
So you would say it's maybe a necessary tool in your product development life cycle as it stands now?
Yeah, it's very high bandwidth, very good value for money. These sorts of scopes in real time are hundreds of thousands of pounds with 25 gigahertz of bandwidth. So, and they're small and compact, they don't take up too much room on your desk. Great product, really. Yeah.
Well, thank you. Thank you very much for your time. It was just great to hear from Adrian Carter, one of our senior hardware engineers, how he uses the 9400A in his day-to-day work. Thanks.
No worries.
So we hope you enjoyed that, and we're now going to hand over to Stuart Merlis, our RF applications engineer, to do some live demonstrations for you.
Well, a very good morning. Thank you for the introduction, Gemma. Yeah, for the next little while or so, what I'm going to do is just go through some of the key benefits of using the 9400A in terms of its functionality. I'm just going to guide you through what I have on the as a setup. What we're going to do here is we're first going to characterize a very high pulse, high speed pulse as our first introduction to the SXRTO. So one of the things we can achieve with this is a very fast rise time, and with significant enough bandwidth, we can actually characterize this pulse to quite a decent level. Then the second demonstration is going to be a high speed demonstration looking at PCI Express. In terms of my setup, I've got a differential data line going into channels 3 and 2. Okay, so fully differential pair. You'll notice as well that when I do the demonstration, one of the key benefits of the 9400 is I can trigger off channel, and I'll illustrate that very features. The fact that I can either use channel 2, we're going to use the Agile synthesizer, the AS108, and we're going to look at some modulation schemes that we can achieve with the AS108 and the 9400 and consequently make some measurements. Right, so on the screen you will see our first demonstration, and this is the fast edge of the pulse generator. So measuring a fast edge with an oscilloscope is crucial for characterizing digital signals, pulses, and the performance of high-end speed electronic circuits. What we need to do is break down of what a fast edge measurement entails and the key considerations. So ideally, what is a fast edge? A fast edge refers to a rapid transition in a signal's voltage level, typically from a low state to a high state, rising edge, or from a high state to a low state, falling edge. The speed of this transition is quantified by its rise time, or a rising edge, or fall time, or a falling edge. Rise time, TR, the time it takes for a signal to go from 10% to 90% of its true amplitude, or fall time, TF, the time it takes for a signal to go from 90 to 10% of its initial amplitude. These measurements are critical because they indicate how quickly a circuit can switch between states and are closely related to the signal's bandwidth. A faster edge implies a wider bandwidth, as it contains much higher frequency components. So what we would do is, why would we measure these fast edges? It is crucial in digital signal integrity. In digital signals systems, for example, fast edges are essential for reliable data transmission. Poor fall times can lead to signal degradation, symbol interference, and timing errors. Circuit performance. The rise and fall time of a circuit's output can indicate its speed capabilities and limitations. Component characterization. Engineers use fast edge measurements to characterize switching performance of transistors, logic gates, and other high-speed components. And also, troubleshooting abnormally slow or distorted edges can point to issues like excessive capacitance, incorrect termination, or component fails. So on the screen now, you'll see I have a very fast edge. What we're going to do now is we're going to fully characterize this. You will notice here my time base is set at 5 nanoseconds per division, and I'm actually on channel 4. On channel 4. On channel 4, I'm triggering off the signal. So what we're going to do is now is make a measurement, and you can see now I'm going into my measurement menu. By left clicking the mouse, you can either bring the menu structure for that on the left. If I right click the mouse, it will appear on the right hand side. So if I now go to statistics, I'm now going to look at a rise time measurement. Okay, you can see there we have got a rise time measurement of about 16 picoseconds. What I would like to do now is show you some of the other features where I can literally zoom into the signal. And what we're going to do now is maybe look at some of the ringing involved in there. And you can see now I'm actually looking at the characteristics of the signal. Okay, you'll notice as well that because we're using the 9404A-25, which has an intrinsic rise time, I'm able to measure the complete rise time of the pulse generator and the scope's rise time. Right, so what I'm going to do now is going to quickly explain a couple of other things that are critical best practices for success. First of all, impedance is king. Always 50 ohms throughout the entire signal path. Pulsar output, cable, oscilloscope input. Any mismatch will cause reflections that distort the true edge. Cable quality and length. Use microwave grade low loss 50 ohm cables. Keep them as short as possible. Long cables and cheap cables will significantly degrade your rise times. Here at Pico, we have a range of accessories that are specified cables that are specified for use with our 9400A series range of oscilloscopes. Minimal adapters. Avoid adapters if possible, and if you must use them, use high quality precision RF microwave adapters. Calibration, ensure you is within the calibration cycle, the environment, stable room temperatures. By meticulously following these steps, you'll be able to accurately measure and visualize incredibly fast edges generated by pulse generators. Now we're going to go on to a high-speed data application. So I'm going to just turn this off, and show you how quickly and effectively we can actually look at high-speed data. In this example, we're going to be characterizing or fully characterizing a PCI Express. Okay. So now if I know, you'll notice I'm going to trigger on channel 2. Okay, so we have our PCI Express data there. Along here, you can see the controls. I'm going to change the time base. Okay, and now we can start looking at it. Because it's a differential pair, what I'm going to do is actually create a maths channel. The maths channel will allow us to actually make a differential signal, and we will then build up a mask, make some measurements. So now if I go into maths channel, again, shows you the functionality within the software. So now I'm going to go 2 and 3 as my operand and turn this on. And if I subtract, there we can see that you'll notice now that there is a significant difference between the original, the differential pair. I just got to scale it accordingly. Okay, so if you notice there, if I now take that to 200, you'll see that we now are going to actually acquire and wrong one, excuse me, finger trouble there. Okay, so now all I've left with is my differential pair. Okay, I'm just going to widen the time base a little bit there. And what we're going to do now is go into iDiagram and start making some measurements. So first we'd want to see our bit rate. And here I need to go to F1 in this case, because now we're looking at a differential signal. Okay, and we're also going to look at frequency. Okay, so you'll see there this PCI Express data is at 3.3 gigabits per second. The frequency is 1.66. So if we were to look at a pre-compliance application, you would see that we actually are, we're building up a picture, a story of the signal. And now we'd want to now look at our jitter. Okay, so you can see there now we're also building up a jitter. The signal is very clean, considering it's off a board. You've got a peak-to-peak jitter of 21.5 picoseconds and an RMS jitter of 2.8. So my next evolution in the process now would be to is have a look at this signal. Okay, I'm now going to go into mask tests. One of the things we can do here is pull down a range of masks in this example. So we've got ANSI, we've got Ethernet, we've got fiber channel, we've got InfiniBand, we've got PCI Express, which is the one I'll be activating in due course. We've got SFF, we've got Sonnet, we've got Serial 88, even USB. So in this example, we're looking at PCI Express. Okay, and we click build. Okay, now what I'm going to do is click alignment, and there you can see I've aligned my mask to that. So what we can do now is look to make sure, and you can see there we're slightly in, when we look at the one eye, we're slightly in in breach of the violation. Now if we were to look at the original waveforms together, which I'm going to turn on now, again you can see there that we're slightly off misalignment there. So I could then, what I could possibly do is just adjust my time base and go this way there, but you can see we've got a slight bit of noise sitting on the waveform there. So in this example, we're hitting the mask. Just going to turn off my mask channels. There, the edge is quite tight there. So this is how typically when we're looking at high-speed signal integrity measurements, these are the steps we would go through to achieve the measurement. The last thing, but we might want to do as well, is set up some actions for these measurements. So if I go into mask test here, I can actually count the number of waveforms. So I can set the number of waveforms to 125 or 1,000, and we can actually save that data to disk. So you can see that the 9400A Pico sample 4 has a really good set of features in terms of mask limit testing. So now I might want to look at the individual channels. You can see there, or if I wanted to just turn on that one there, you can see the individual channels. Now channel 2, you can see there, I can see that, the individual channels. The third The third demo I'm going to show is using the AS108 as previously described. So we can turn these two off and we can actually look at some modulation schemes. So if anyone has any questions with regard to mass limit testing with PCI Express, feel free to phone in as usual or contact us and we'll happily set up some demonstrations, etc., etc. I'm now just going to clear this, and then our last demo is going to be using, as I said, the Agile synthesizer, the AS108, to create some modulation schemes. So, mask. So now you'll see I've now got channel 1 enabled. Okay, and just going back to my setup, you'll see I'm going from my signal generator output. Again, one of the features of the 9400A is the fact I can trigger straight off channel. So now I'm going to go to channel 1, and I'm hoping you can see that we're just to bring up the menu structure of the PicoScope card, and you can just show you my modulation scheme. And what we're going to do is just have a quick look at how a modulation scheme could be beneficial in characterizing modulation schemes. So what I'm going to do now is just reduce my level. Okay, let's clear that. Right, so what we're going to do to start with is an AM scheme. If we go to the synth module there, you see I've got this is a 3 gig signal. Okay, and I'm just going to make that 200 millivolts per div. This is a 3 gig signal, and I'm going to pull this over a little bit so people can see it there. And if I go back to my carrier wave, I'm going to select amplitude modulation. Okay, and if I clear that, okay, you can see now that I can set a carrier wave of 1 gig up to 8 gig, the range of the AS108, and I'm going to now you'll see I'm going to reduce now, give it some measurements. So if we now go clear all measurements and go peak to peak, min and max, but pull up my and now I'm going to reduce my mod depth. For anyone who's aware of amplitude modulation schemes, you'll see that I'm at 90% modulation depth. But as I reduce it, you can see now I'm going to clear that. You can see now I'm practically just showing you a 1 gig wave. You can see that the SXRTO can actually quickly and significantly see the mod schemes. So what we can do now is actually increase in frequency. So now I'm going to go to 3 gigs. Okay, so and if I go back to my synthesizer here, I'm now going to increase my mod depth all the way up to 50%. Okay, and you can see as we go along, I'm increasing my mod depth. And if we look at the numbers, which I'm going to do now, I'm going to clear all these measurements and go to channel 1 and go to min and max. Okay, go to min and max, and you can now see my mod depth variations from top and base. Now you can see that. So the just keep in mind as well, if any of your customers need to emulate modulation schemes, the AS108, the Agile synthesizer, is a formidable combination with the SXRTO. Last but not least, I want to just give you an example of some other waveforms that we can acquire with the 9400A. So what I'm going to do now is these are ones I prepared earlier. Okay, so within the AS108 functionality is the ability to pull in waveforms. So, okay, I'm just going to bring in this one here, and it will load it in to the actual software. So I'm going to clear my waveforms and just bring this in here. And there you can, what I'm actually emulating there, it's going to just pull this over. Okay. And what we're actually emulating there is a full sweep and hop of an RF carrier, and it's doing a hop of on a range of frequencies. So we're doing a phase a phase and sweep. We could also do a bi-directional sweep if we wanted. So you can see the AS108 is quite formidable when we're stimulating circuits, RF circuits. In the second part of this, in the second webinar, we'll be going into a lot more in-depth measurements. But from my side, thank you very much. I hope this was a useful insight. Any questions, feel free to contact us. Thank you very much, and I wish you a good day.
Wonderful. Thank you, Stuart and Tim, for a great training session. And we hope everyone that's attended has enjoyed it and that it will give you some confidence whilst promoting our PicoScope 9400A series. Just want to mention that on the bottom right-hand side of the screen, you should now be able to see the download of the slides today. So if you'd like to download them, you just hover over it and press the little download icon, then you can use them. We've got one question that's come through, so I'm just going to turn my camera on and ask Stuart and Tim to turn theirs on as well. Hello, everybody. Just make sure you know that we're live people here as well. So yes, we've had one question come through, which I'm hoping probably Stuart can answer, which is, could you measure the rise time of a PCI Express signal?
Yes, and I can. Yes, I should have done it in the live demo, but yes, 100%. The PicoSample 4 allows you to measure the rise time. Thanks, Simon. And I can't.
Lovely, thank you, Stuart. And that's the only question we've had through, so I just want to say thank you for everybody attending. If you didn't manage to download the slides, then they'll be available within the next 24 hours, we hope, as well as a recording of today's webinar. And as Tim said, our second part will be on the 8th of July. I'll be sending out the information about that soon, so we hope you can all join us for that too. Take care. Thank you, everybody.